It is my great pleasure to introduce today's speaker, Professor Pablo Jarillo-Herrero from MIT Physics. Pablo's research interest lies in experimental condensed matter physics and quantum materials, in particular electronic transport and optoelectronics in 2D materials and other van der Waals heterostructures. His outstanding and groundbreaking research in these fields have led to many, many prestigious awards and honors, and here I would like to just highlight a few. Pablo has been the recipient of the 2020 Wolf Prize in Physics, the 2020 APS Oliver Buckley Condensed Matter Physics Prize, as well as the 2021 US National Academy of Science Award for Scientific Discovery. It is our great pleasure to have Pablo here with us today to learn more about his work in the field of magic angle graphene. Before I turn it over to Pablo, I would like to just remind our audience that they can ask their questions directly by raising their hand at the end of the talk. So you can raise your hand, we'll unmute you, and you can directly ask your questions to Pablo. But if you prefer, you can also use the Q&A feature of this webinar, and we can help moderate the questions. With that, Pablo, thank you again for being here today, and I'll turn it over to you.
Thank you very much, Farnaz, and thank you also Vladimir and Cherise for the invitation. It's really a great honor to speak for the MA-TBG talk series. I want to tell you about today about our relatively recent research on magic angle graphene and how it has become, as I point in the title, sort of the twist and shout of quantum materials a little bit. I hope you will understand what I mean in a moment. But before I dive into magic angle graphene, let me tell you first a little bit about strongly correlated states of matter in general, okay? And the thing is that among the most fascinating states of matter that we have in the universe are those where the interactions between the individual constituents that form that matter are very strong, okay? This is something that happens, for example, in the quark gluon plasma, which is a state of matter that occurs a few hundreds of nanoseconds, microseconds after the Big Bang, and that we can recreate nowadays in heavy ion accelerators such as Brookhaven National Laboratory. We can also find these strongly correlated states of matter in the different phases of nuclear matter in neutron stars. This is a picture of a neutron star by the Chandra X-ray Observatory. And if you go to Wikipedia, you can see that these neutron stars are formed of layers with different phases of matter. They call them nuclear pasta. So as usual, the astrophysicists are very creative. So these phases have names like the lasagna phase, the bucatini phase, the spaghetti phase. So very creative. And perhaps a bit closer to my heart, are the different topological states of matter that one can find in condensed matter systems. So for example, if you take a two-dimensional system of electrons in 2 dimensions and apply a high magnetic field, you can realize the fractional quantum Hall effect, in which, due to the strong interactions between the particles, things like fractional light charges and different types of topological properties of matter arise due to these interactions. So this is something that is present in all areas of physics. And zooming in a little bit more in particular into strongly correlated quantum materials, okay? This is a large family of materials, and perhaps the most studied of all these materials are the high temperature cuprate superconductors, where in a phase diagram of temperature versus doping, there are many phases here that few of which we have a good understanding to this day, as I will mention a bit more later. Now, before I tell you a bit more about quantum materials and correlations, because this is a general talk, let's try to first, from a very simple point of view, what does quantum mechanics tell us in single particle physics, ignoring correlations, about the electronic behavior of materials, okay? So if you take single particle quantum mechanics, single particle band theory, essentially you can have 2 types of behaviors, okay? You have a material that, here's the density of a state. So how many electronic levels we have available per unit, energy as a function of energy. And this material may have these 2 bands, okay? They're separated by this band gap. Well, if it turns out that this material, has one of these bands completely occupied by, with electrons, and the other one completely empty, Turns out quantum mechanics tells us this is an insulator. Okay? And the reason is that if you want electrons to be excited to a nearby free available energy state by a bias voltage or by temperature to conduct electricity, you just can't because you have this band gap. Okay? So this is an insulator. If on the other hand, we have a material which, similarly to before, we have, this is the density of states, these are the bands, okay? And now one of the bands is completely occupied with electrons, but the other one, let's say, is half occupied with electrons, so that your Fermi energy, is here. Now you can see that we have at infinitesimally low energies, we have free available energy states for electrons to be excited via a bias voltage or via temperature so that the material can conduct. And this is a metal, okay? So essentially from single particle quantum mechanics point of view, all materials are either metals or insulators, and that depends on whether, one of the bands is partially occupied or all of the bands are just fully occupied or fully empty. Huh? Now, the moment we introduce correlations or strong interactions between our electrons, the situation can be more complex. For example, we can be in a situation similar to this one, where we have one band which is half occupied with electrons. Okay? But now, due to strong Coulomb repulsion between your electrons, that band splits into two, okay, with a correlated gap in between, okay, with a band gap, but with a gap, but it's not a single particle band gap, but a correlated gap in between these two bands. But you can see that because this band was occupying half of the total band, this splitting into two bands now leads to a situation which is very reminiscent, very similar to this one. You have one band which is completely occupied and one band which is completely empty, and there is a gap in between. And therefore, the system actually goes into an insulated state, but it's not due to single particle physics, it's due to correlations, okay? Now, there are different examples of correlated insulators, okay? One of the most famous is the Mott Insulator, which is the parent compound of the High-T Cuprate Superconductors. So now the Cuprate superconductors, the key element is this copper-oxygen plane, where when you have a stoichiometric compound, you have one electron per copper atom. You could have up to 2 electrons per copper atom in that orbital, spin up and spin down, but you have 1 electron per copper atom. You are half occupying, that system with electrons. And it turns out that due to the strong Coulomb interactions between these electrons, the electrons get stuck in their locations and they cannot conduct electricity. It's an insulator. Okay? Now, an interesting thing happens as you remove a few of these electrons by chemical doping, okay? We say that we dope it with holes. Now, because some sites are empty, these electrons can actually jump from here to here. They're no longer being repelled by the existing electron here. And now, the way those electrons start to jump in a correlated fashion between all these sites gives rise to superconductivity, okay? Now, we believe that the essential physics that is contained in the superconductivity in the high temperature Cuprate superconductors is described by this model called the Hubbard model, where you take into account that charging energy or repulsion of putting 2 electrons in one site. And you take into account also the tunneling between sites, when one of those sites is empty. But now I say that we believe that this contains the basic, the essential physics of high temperature Cuprate superconductors, because this model, the Hubbard model, even in the simplest of implementations, cannot be solved theoretically, despite more than 35 years of intensive research on this model. So this leads, how do we go from here to here is still a mystery. And in this phase diagram of the Cuprate superconductors, but also many other correlated materials, okay, very few of the phases that we find here are actually completely understood theoretically. Now, these difficulties to understand, essentially the physics of strongly correlated systems have led to real, other alternative approaches to try to see if we can get insight into these systems, okay? And one of the most exciting ones are that of, is that of using ultra cold atoms in optical lattices in order to investigate strongly correlated quantum materials. So if you take 2 lasers and you shine them at each other, okay, then you can create a periodic potential for atoms. You can load this periodic potential with atoms. And it turns out that, the atomic physics people have a very nice knob with which they can tune the interactions in the system, so that already back in 2002, they were able to realize a transition between a Mott insulator and a superfluid, okay? That was using atoms which were bosons, okay, with the integer spin. So that was a realization of the Bose-Hubbard model. A few years later, they were able to realize this with fermionic atoms. So that was a realization of the Fermi-Hubbard model. And just to give you an idea of what's the latest, the state of the art in the community is that as of a few years ago, they have been able to realize antiferromagnetism in this Fermi-Hubbard model, okay? So they can load, they can load their lattice with spins, and they can look and see that at low temperatures, the spins order antiferromagnetically, spin up, spin down over short ranges. Yeah? So this cold atoms community is starting to explore this corner of this phase diagram, you know, Mott, antiferromagnetism. They would like to explore the entire phase diagram, and in particular, see if they can reach, you know, D-wave superfluidity due to repulsive interactions. But that turns out to be very challenging because they have to go down in temperature quite a bit. Okay? They're already working at a nanokelvin or so, and they have to go quite a bit lower in temperature in order to reach this region. Okay? So while there's no, you know, fundamental obstacle to it, it's a very serious technical challenge. So what I want to tell you about today is about, you know, a new platform for strongly correlated physics. Okay, so we have the actual quantum materials with typical lattice scales of a few angstroms. Okay, here is a high temperature Cuprate superconductor, for example. We have also ultra cold atoms in optical lattices. Here, the distance between these atoms in this lattice is typically of 1 micron. And today I want to introduce magic angle graphene and related, you know, by now this is just an example of a large family of what are known as Moiré quantum systems, where this superlattice length scale is of order 10 nanometers. Yeah? Now, associated with these length scales are energy scales, you know, temperature scales or energy scales. So in quantum materials, we typically have temperature scales of the order of 100 or 1,000 Kelvin. In cold atoms, these temperature scales are 0.1 to 1 nanokelvin. Magic angle graphene and similar Moiré systems, because the lattice scale is, you know, a couple of orders of magnitudes from either of these, the temperature scale is also a few orders of magnitude in between these, okay? But this is a very comfortable energy scale to explore in the laboratory. So with this introduction, let me tell you, this is the outline of what I want to tell you about today. Yeah? First, I'll talk about the twist, about 2D materials, Legoland, Twistronics, various terms you may have heard, and a little bit, I will introduce the graphene and in particular magic angle graphene superlattices. And then I'll tell you, you know, what became the shout, which was, you know, our discovery of correlated insulator behavior and superconductivity. And then I hope to have a few minutes to tell you about the latest, including, you know, very exciting recent work, which I think is of interest to the whole of MIT.nano community. So let's tell you, you know, let's look a little bit at the twist, okay? So now over the past, you know, 15, 16 years, we have been having a lot of fun investigating a variety of two-dimensional materials, okay? The first one, which was isolated, was graphene, but then plenty of others came to the market. And we've been having a lot of fun looking individually at each of these materials. And then soon after, people realized that, hey, these are two-dimensional materials, so we can put them on top of each other, similar to Lego pieces stacked on top of each other. Yeah. Now, this is something that you can also do when you grow, for example, semiconductor heterostructures. You can put different materials on top of each other when you grow with MBE, for example. However, an advantage of 2D materials is that I can put whatever I want on top of whatever I want without having to worry about lattice mismatch compatibility or about chemical composition compatibility. These are van der Waals materials, and I can stack them on top of each other. Now, this is, this led to my friends and colleagues to write these review papers about, making an analogy between 2D materials and van der Waals materials and Lego pieces. Now, while this Lego aspect is an important aspect, okay, I don't think it is the most unique aspect of 2D materials. In fact, Lego pieces, I don't know how many of you have played with Lego. I have small children, so I play with Lego all the time. And, sometimes my kids come and tell me, Daddy, I can't stack this piece on top of the other. I have to tell them, look, that's because you have to rotate them to exactly 0 degree angle of rotation between the pieces. Only then you can stack them on top of each other, okay? So while this Lego aspect is an important one, perhaps the most important aspect of 2D materials, or the most unique aspect of 2D materials, one for which there is no precedent in the history of material science is the following, is the fact that we can do this. We can put two-dimensional crystalline lattices on top of each other with an arbitrary angle of rotation, any angle that we want. It can be 50 degrees, 21 degrees, 1.1 degrees, why not, as I will show you in a moment, okay? And this can result in a dramatic modification of the electronic, optical, mechanical properties of the system, okay? This is something that we could not do before. It's a highly non-equilibrium form of matter, but is metastable enough that we can actually perform many experiments. So we can do this, okay? And as you can see, what happens when you stack two-dimensional crystals on top of each other with an angle, with a twist angle, okay? This is something that people have called Twistronics, is that you form a Moiré pattern, okay? I'll tell you a bit more about that. So, all right, let's look a little bit at graphene and magic angle graphene superlattices. So I think most of you are familiar with graphene. I'll just very briefly comment. So graphene is a honeycomb of carbon atoms. All of these atoms are chemically equivalent. They're all carbon. However, from the crystallographic point of view, they are inequivalent, okay? In order to tile a honeycomb, you need a two-atom basis in addition to your unit vectors. So we label these atoms, you know, A and B, or red and green. And we speak of the A and B sublattices, okay? Now you can calculate in a simple quantum mechanical model what is the electronic structure of electrons in graphene. This is energy versus momentum in the X and Y direction. And it has this very unusual electronic structure. Near the Fermi energy, let me zoom in, we have these famous Dirac cones, this famous, you know, energy is linear in momentum, okay? This is very atypical. For most materials, kinetic energy is quadratic in momentum, okay? But for graphene, electrons in graphene is linear. And this has made, this has resulted in plenty of analogies when we study graphene, you know, the fact that electrons in graphene behave like ultra-relativistic particles, similar to the way, this is the same energy momentum dispersion of photons into dimensions. In fact, this relationship, we can write it in Hamiltonian form. This will be the only formula in my talk, so don't worry. This is nothing else but the Dirac equation in 2 dimensions for massless particles. Okay? Energy is linear in momentum. Now in the Dirac equation, this is a spinor, which typically tells you whether the spin of the electron is up or down. Here in graphene, this is a pseudo spin, which tells you, pseudo-spinor, which tells you whether the electron wave function is on the A type of sublattice or on the B type of sublattice, okay? Now, the only other thing that I need you to remember from graphene is that there are 2 independent valleys, or these Dirac cones, we call them valleys. They're called the K and the K prime valleys. So electrons in graphene have this 4-fold degeneracy, spin up and spin down, valley K and valley K prime. Just remember the number 4. It will appear later in the talk, okay? Okay, so now what happens if you put graphene on top of graphene and you rotate, okay? As I mentioned earlier, a Moiré pattern forms, and the Moiré wavelength, the distance between these soccer balls that you see on the screen, depends on the twist angle, okay? It can get all the way to infinity because these lattices are identical. I'm just placing graphene on top of graphene, yeah? Now let me stop this before you get a little bit dizzy. So this is, what happens when we twist, when we put graphene on top of graphene from the point of view, the Moiré pattern forms in real space, what happens in momentum space, and also to the electronic structure, okay? So if we take here graphene, this is the electronic structure, the zoom in of the Dirac cones. This is the first Brillouin zone. If you have your Fermi energy at some finite value here, you have your Fermi surface is a disk, okay? And you have only 2 of them, K and K prime. The others are just copies, okay? But reciprocal space lattice vectors. So now let's put graphene on top of graphene, okay? If we perfectly align them in real space, the reciprocal spaces are also aligned. If we rotate in real space, the reciprocal spaces also rotate. And that means that the Dirac cones of layer 1 and layer 2 become separated in momentum space, okay? That separation is proportional to the sine of the rotation angle divided by 2, okay? Now, let's start from a small rotation angle so that, this sine is already equal to the angle, and let's see what happens to the electronic structure. Yeah? So if we start from a small rotation angle, the separation between these 2 Dirac points is proportional to the angle. Now, this would be the electronic structure if the electrons in one graphene sheet didn't know that the other graphene sheet exists. However, when we place graphene on top of graphene, these two sheets are just 3 angstroms apart. Okay? So electrons are very much aware that the other graphene sheet exists, and in particular, they can tunnel between the 2 sheets. This leads to bonding, anti-bonding states, okay, due to this interlayer tunneling or interaction, okay, so that the gap opens with one band being pushed down in energy and the other band being pushed up in energy. Okay? You can think of this as the same thing as bonding and antibonding states in a hydrogen molecule, except that now it's a giant graphene molecule, 2 graphene sheets coupled. Okay. Now this is the situation when this gap, okay, this interlayer interaction is much smaller than the energy of that crossing point. But if we twist now towards smaller and smaller angles, these 2 points get closer and closer, and this gap, this band, this lower band, gets pushed down to lower and lower energy until it touches 0. Okay, that touching of 0 is, we say that a flat band condition has been realized, has been reached, and that occurs at an angle called the magic angle. Okay, and that magic angle is 1.1 degrees. Okay, there was theoretical work, about a decade, ago, which predicted this magic angle of 1.1 degrees. Okay, and that's for graphene on graphene. Different materials have different angles. Now, this is a cartoon. Okay, let me show you. This is an actual calculation of the electronic structure of magic angle graphene at 1.1 degrees. Okay, as you can see, there is this set of flat bands. That's the flat band condition. These are the other remote bands in the band structure. And these flat bands, okay, they're not completely flat. There's a little bit of dispersion, but they're much, much flatter by orders of magnitude than the original graphene electronic structure. Now, how do the electrons look like? If we put electrons in these bands, where do they like to go? Okay, for that, you just have to do a Fourier transform. Remember, flat in momentum space, in reciprocal space, means highly localized in real space. Okay, you have to do a Fourier transform to go from one to the other. So if we place electrons in these flat bands and we look where do they like to be, okay, it turns out the electrons, they like to accumulate in regions which are called of AA stacking, where locally the registry between the 2 graphene sheets is such that all the carbon atoms are on top of each other. These regions are separated by regions where locally, due to the small twist angle, the registry is such that the stacking is of AB and BA type. Only some atoms are on top of the other, okay? And those are tunnel regions, regions with coupled via tunneling, the AA regions. So from the top, we have something, magic angle graphene looks like this. We have these regions of AA stacking where the electrons like to sit. And these regions are separated by regions of AB and BA stacking where the electrons do not like to be. Okay? In a slightly more realistic schematic, this is what you have. You have these yellow regions of AA stacking where the electrons like to be. This is what's going to form our triangular Fermi-Hubbard lattice by analogy with the cold atom systems, okay? And the separation between these AA regions is of order 13 nanometers. Now, I put in quotes here triangular because in reality, this is a honeycomb lattice, because you have these A and BA regions, okay, which are not identical. And there are also interesting topological properties of this system, which make it different from a regular Fermi-Hubbard lattice, okay? But that for the experts. So now, okay, and here comes now the shaft, or the beginning of the shaft. We make devices, okay? And you can ask me later if you want, how do we make these devices? But let me just skip that for a moment. And we make devices where we have magic angle twisted bilayer graphene. Okay, so twisted bilayer graphene at this angle 1.1 degrees. It's encapsulated between 2 dielectrics, 2 flakes of hexagonal boron nitride. It's a very nice dielectric for the system. We can attach source and drain contacts so that we can apply a voltage and measure a current. And we have a nearby metallic gate electrode to which we can apply a gate voltage to change the charge density in the graphene. This is essentially a field effect transistor geometry, which I think most of you in the audience know what it is. Okay? So we form a parallel plate capacitor and we can change the density in one of the layers of the capacitor, which is the actual magic angle graphene. So now let me remind you, how does conduction through graphene look like? Okay? Just regular graphene. Okay? If you look at conductivity versus charge density, if you have your Fermi energy here deep in the valence band, you have lots of holes and graphene conducts very well. If you put your Fermi energy deep in the conduction band, you have lots of electrons, and graphene conducts very well. In fact, it's the best conductor in the world, okay? If you put the Fermi energy at the charge neutrality point, there are very few charge carriers, and graphene conducts poorly. So the conductivity of graphene versus density has this V-shaped behavior, okay? And this has been seen by thousands of groups around the world. Let me show you now how does it look for magic angle graphene. Yeah? So here we have conductance for an actual magic angle graphene device versus charge density. This is charge neutrality. You can see that near charge neutrality, the system still remembers its graphene, so it has this V-shaped conductivity, but check what's happening at all of these other regions. You know, and the conductivity goes to 0 in many places, okay? So what is that? This is the electronic structure of magic angle graphene. Turns out, remember that I told you that in these flat bands, okay, the graphene, electrons in twisted Bilayer graphene, they can have this fourfold degeneracy, spin up, spin down, valley K prime. We also have 2 layers. It turns out in these flat bands, you can put from bottom to top of these flat bands, you can put 8 electrons per Moiré unit cell, okay? So if we add to the system 4 holes per Moiré unit cell, or remove 4 electrons from charge neutrality, your chemical potential ends here. And as a result, because your chemical potential is in the middle of a band gap, you have a single particle insulator behavior, okay? This is exotic, but well understood in terms of single particle physics. The same thing happens if you put 4 electrons per Moiré unit cell, okay? Your chemical potential goes here, you're in the middle of a band gap, and you have a single particle insulator. The interesting thing happens now, if you add 2 holes per Moiré unit cell, your chemical potential, your Fermi energy is now in the middle of a band, of the valence band. The system should be an extremely good metal, okay? And on the other hand, the system is an insulator. The same thing happens if you put 2 electrons per Moiré unit cell. The system should be a very good metal. Instead, it is an insulator. These insulator states that happen when the Fermi energy is in the middle of a band are correlated insulator states, okay? Due to Coulomb interactions between your electrons. Now, this type of behavior where you have these correlated insulator states only happens in a relatively narrow angular range around these 1.1 degrees, okay? So we have measured, you know, here for devices, we've measured many, you know, by now dozens and dozens of devices. Only when your twist angle between your structures is between 1 and 1.2 degrees, more or less, that's the margin, 1.1 plus minus 0.1 degrees, more or less, you have this correlated insulator behavior. So it's very tightly coupled, intimately connected to these flat bands that occur at the magic angle. Now, let me tell you more, okay? So when we were measuring these devices, you know, we were, you know, looking at the correlated insulator state behavior here, okay? We were doing temperature dependence. These are all low temperature data. And we saw that, you know, as we cool down from here, from 1.7 Kelvin to 0.3 Kelvin, we see that the system conducts less. And that's what you expect from an insulator. The colder it gets, the lower the conductance, okay? If you look around the correlated insulators for electrons, same thing happens here. The colder it gets, the less it conducts. However, if we just add a few extra holes to the system, it seems like the colder it gets the system, the better it conducted, okay? So that conductance enhancement was kind of unusual, okay? And now these devices that we made before, they were measured in a, you know, the devices that we fabricated had a 2-terminal geometry measurement, yeah? And that, a 2-terminal geometry. And that is because if you're gonna measure an insulator, you don't care if you have a parasitic series resistance, you know, infinite resistance plus parasitic resistance is still infinite. So if you want to look for insulators, which is what we were looking for, you know, it's okay to have a 2-terminal geometry. Now, if on the other hand, you want to measure how well something conducts, and in particular, if it might be a superconductor, you want to eliminate all that parasitic resistance, okay? So you want to make devices in a 4-probe device geometry, okay? So we made similar devices, okay, just with, you know, 4-terminal, in this case, actually 6-terminal whole bar geometry, so that we can run a current through the device and measure intrinsically the voltage dissipated, the energy dissipated in the bulk of the device, okay? And we made devices, and lo and behold, to our great surprise, magic angle twisted bilayer graphene superconducts, okay? You have data here for 2 devices. By now we have dozens and dozens of these devices, okay? The resistance versus temperature experience this precipitous drop to 0 below our noise measurement floor. The system is a superconductor. You can in fact do any test of 2-dimensional superconductivity that you want, okay? For example, you can run a current, finite current, you see 0 voltage dissipated until the moment the system switches to a resistive state. You can apply magnetic field, I'm not showing it here. You can also do Josephson phase coherence experiments. This thing is a 2-dimensional superconductor. And not only that, the system is an electrically tunable superconductor, because remember, we have this field effect transistor geometry. So that means that, you know, if we start from these 2 holes per Moiré unit cell, where we have this correlated insulator state, okay? Now we can add a few more holes to the system, and the system has this superconducting dome. If we add a few electrons instead, we go in the other direction and we add electrons, we have another superconducting dome. And we can do this electrically. Now, the moment, you know, my students showed me this data, I was fascinated, because this instantaneously reminded me of the hundreds and hundreds of times that I have seen phase diagrams such as this, okay? This is the phase diagram of the high temperature Cuprate superconductor family, okay? They sort of get the electron doping and hole doping wrong in this diagram. Let me flip it for you. Here it goes. Here it's correct, okay? Now, as I mentioned earlier, 0 dopant concentration means 1 electron per unit cell, okay? In a cuprate, that is a Mott insulator, which is a correlated insulator. You add holes and you get a superconducting dome. If instead you add electrons, you also get another superconducting dome. Here we have at 2 holes per Moiré unit cell, we have a correlated insulator. You add holes and you have a superconducting dome. You add electrons, you have another superconducting dome. Now, a big difference between these 2 systems is that this is a theoretical phase diagram, okay? In order to populate this phase diagram with actual experimental data points, you have to grow hundreds and hundreds of crystals, each with a different doping, each with a different chemical composition, often using different materials classes, because not all doping ranges can be, you know, done with, you know, achieved with the same material. Whereas in this case, I can go from here to here and measure this thing in a few seconds just by dialing a voltage knob, okay? So this is something that, of course, attracted a lot of attention. Now, let me point out that although there are many similarities, there are also many, many differences between the systems, okay? So you should only take this thing a little bit as inspiration. Now, more often than not, we actually see a huge asymmetry between the electron and hole domes, superconducting domes, okay? So it's more often a much bigger superconducting dome for holes and a small superconducting dome for electrons, okay? And in our original discovery paper, the maximum critical temperature was about 1.7 Kelvin. Now we can reach up to 3 Kelvin or so in our best devices, yeah? Now, how strong a superconductor is magic angle graphene, okay? Well, on one hand, I just told you, you know, maximum TC is of order of, you know, Kelvin, maybe even 3 Kelvin, while, you know, high temperature superconductors can reach, you know, kind of superconductivity in the 100 Kelvin range, okay? So what's the big deal? Well, the way physicists compare superconductors, you know, how strong they are, is not based on the actual absolute value of TC, which is, you know, it's very important if nothing else for applications, but we, you know, that's not what gives you the measure of how really strong is a superconductor. What we do typically is compare, okay, how high is the critical temperature compared with how large is the density of electrons that the system can contribute to the superconductivity. And this is something that is typically shown in this log-log type of diagrams, where on one side we have the critical temperature of the superconductor, and on the other side, on the other axis, we have the Fermi temperature, which is basically the electron density normalized by some factors, okay? So in this type of, you know, this is called a Uemura plot. This type of plots, you know, conventional weak coupling BCS superconductors tend to be near this corner, okay? For example, aluminum is a superconductor that has a 1 Kelvin critical temperature, similar to magic angle graphene, but it has a gigantic amount of electrons, okay? The Fermi temperature is over 100,000 Kelvin. So given how large a density of electrons aluminum has, its TC, you know, it's relatively modest, okay? It's only a modest contribution to the superconductivity. Now, the more you go diagonally towards this purple band, the more and more exotic typically the superconductivity becomes. Particularly in this purple band, we have most of the unconventional superconductors, okay? For example, you have here the cuprates family, the high temperature cuprate superconductors, also the iron pnictides, you have the organics, you have the heavy fermions. I included here some data for cold atoms, okay? Both axes multiplied by 100 million so that they appear in this plot, but as you can see, cold atoms can reach an extremely strong coupling strength, it's called, okay? Reaching all the way to the BEC-BCS crossover. So where is magic angle graphene in this diagram? Magic angle graphene happens to be there, okay? Is among the strongest coupled superconductors that exist. If the high temperature cuprate superconductors with superconductors at 100 Kelvin had the coupling strength of graphene, of magic angle graphene, they would be room temperature superconductors, okay? Now, after we published our results, immediately this attracted a lot of attention. In particular, some of the key questions that people have been trying to answer is, what is the origin of this correlated insulator states and the superconducting order parameter? And if you, for those of you that follow the archive, this is just a small sample of the papers that appear within a couple of weeks of our discovery. By now, this list has several thousand papers, actually. All kinds of order parameters have been proposed with all letters of the alphabet, S, P, D, F, S plus P, D plus ID, etc. Okay, I don't want to talk too much about this. There's a lot of activity going on. This also attracted a lot of attention in the popular press. This was chosen as discovery of the year by Physics World. Nature, Quantum Magazine published these very fancy looking pictures. This is actually my favorite with this 1.1 degree clock there. I wish I was able to design this kind of picture, really very fancy, okay? Now, let me tell you a little bit about what has been happening since we announced our discovery, okay? So we announced this at the APS March meeting in 2018, and we published the paper in April. So what has happened since then? So the first thing that has happened is that we have reproduced our own results many times. That's good. It doesn't always happen, so it's good when it happens that you can reproduce yourself. Okay? So by now we have many devices. This is actually quite outdated already, this slide. We're beginning to measure the critical temperature as a function of angle. You see that there's sort of a dome in twist angle now, okay? And we've seen superconductivity roughly between 0.95 and 1.2, maybe 1.25 degrees, okay? So again, in a narrow angular range. Now, better than you reproducing your own results is when other groups independently reproduce your results. Then, only then it becomes real science, okay? And since our discovery, plenty of other groups have reproduced our results. The first one was by a collaboration by Andrea Young and Corey Dean, where they reproduced our results and extended them in very interesting directions, doing pressure studies. The second paper was by Dimitri Efetov and colleagues in Spain, again, discovering new superconducting domes. By now, over a dozen groups have reproduced our results and extended them in interesting directions. Now, since then, we have learned a lot about the properties of this system, okay? The system has a linear in temperature resistivity behavior, which is very reminiscent of the strange metal with physics in correlated systems with Planckian dissipation. It also exhibits anisotropies in, for example, the critical parallel magnetic field, okay, which indicates that the superconducting state is nematic. That means it breaks lattice rotational symmetry, for those of you that know this. We have many other systems now that exhibit correlations when you twist them. The first one after, the second one was after magic angle graphene was magic angle twisted bilayer graphene, 4 layers, one with zero, one pair with 0 degree angle, one pair with 0 degree angles, and now these pairs twisted by 1.1 degrees. There have been many scanning probe microscopy studies, and we have been discovering new and new phases in the system, okay? In particular, ferromagnetism, and we have measured also anomalous Hall and quantum anomalous Hall physics, which indicates that the system has interesting topological physics in it, okay? Now, in fact, one of my biggest joys is that these correlated Moiré heterostructures have meant the merging of several modern condensed matter physics communities, okay? On one hand, we have the two-dimensional vast materials and heterostructures community, people looking at graphene, etc. On the other hand, the people that traditionally were looking at strongly correlated materials, cuprates, pnictides, etc. And then the people that do topological condensed matter physics, quantum Hall effect, topological insulators, etc. They all come together in this area of correlated Moiré heterostructures. In fact, soon after our discovery, together with our colleagues, our theory colleagues, we predicted that there would be nearly flat Chern bands, meaning topological quantum anomalous Hall physics in a variety of Moiré systems. Okay, a few months later, this was realized by the group of David Gohaber-Gordon showed that there was ferromagnetism, showing here large anomalous Hall effect in magic angle graphene aligned to hexagonal boron nitride. A few months later, the group of Andrea Young showed that there was this quantized anomalous Hall effect in a beautiful experiment. The group of Feng Wang at Berkeley showed that a different Moiré heterostructure, ABC trilayer aligned to HBN, also exhibits very similar type of quantization. And by now we have many systems that do this. Okay. Something that has happened very, very recently, as of a couple of weeks ago, is that we have realized a second robust Moiré superconductor. Up until recently, it was only magic angle graphene that was a robust superconductor. But now we have another one. It's called magic angle twisted tri-layer graphene. Instead of bilayer, they tri-layer. Okay. And this was just published a couple of weeks ago. I call this Moiré Magic 3.0. Okay, 3 layers. It turns out that when you put 3 layers arranged with special angles, also magic angle, which is different from the previous magic angle, okay? Magic angle depends on the number of layers. You have an extremely strong superconductor, even stronger than the bilayer case, okay? Close to the so-called BCS-BEC crossover. And it's also extremely tunable, not just with charge density, but also with the transverse electric field. It's the most tunable superconductor that exists in the world, okay? And, the group of Philip Kim published in the same week, we published in Nature, they published in Science, these papers came out the same week. So this has been instantaneously reproduced by another group, okay? Many more surprises are gonna come out of this system soon. Now, I hope to have convinced you that there's quite a bit of magic in this Moiré quantum matter, okay, or these Twistronics systems. So we basically are finding slowly a lot of the phases of matter in the system: correlated insulators, superconductivity, topological phases, magnetism, nematicity. Now, what about one very, a very traditional and very useful, for applications state of matter, ferroelectricity, okay? Can we find more ferroelectricity? Well, as of a couple of months ago, fresh again, we have, our own group together with 2 other groups have discovered this Moiré ferroelectricity. There was also interesting work before related work by a group at Columbia showing piezoelectricity. Now, what do I mean by Moiré ferroelectricity? Okay, so, 2-dimensional ferroelectrics are very rare in nature. Okay, so I think actually all of those that exist are here in this slide. Okay, there might be a few others I missed. Okay? Basically, all of these ferroelectric 2D materials are obtained by exfoliating bulk polar metal. So in some sense, you come from a bulk polar metal, which was non-centrosymmetric, which probably was ferroelectric, and you thin it down to 2 dimensions and it becomes ferroelectric. This is an interesting but relatively trivial way of getting ferroelectricity in 2 dimensions. You just come from something, which already was prone to ferroelectricity in 3 dimensions. By Moiré ferroelectricity, I mean something different. I mean, in the same way that graphene is not a superconductor or an insulator, but when you twist it, when you put it on top of each other and you make a Moiré system, you can have a correlated insulator or superconductor. Now we can obtain ferroelectricity out of a material that in the bulk is not ferroelectric, okay? So in the system that we chose to do this, there are many more, potentially, is bulk, is hexagonal boron nitride. So bulk hexagonal boron nitride has, hexagonal boron nitride is a honeycomb lattice also, where you alternate boron and nitrogen atoms. It's like the graphene where the A and B sublattices are now boron and nitrogen atoms, okay? So now they're chemically distinct. And it typically, the stacking in the bulk, if you grow a crystal, is AA prime, meaning the boron atoms are on top of the nitrogen atoms and the nitrogen atoms on top of the boron atoms. They're exactly aligned, okay? That's a bulk. This means that for a bilayer of bulk hexagonal boron nitride, the natural stacking has HBN layer 2 rotated by 180 degrees on top of HBN layer 1, okay? And this is a centrosymmetric arrangement, no ferroelectricity. Now, since we can place two-dimensional materials on top of each other arbitrarily, we can do something, which is we can make highly non-equilibrium hexagonal boron nitride bilayer. What do I mean? I mean the following. Let's take a monolayer of hexagonal boron nitride. And now I put here, guide to the eyes for each of the atoms, boron and nitrogen. And now let me split it in two and parallel stack it on top of itself, okay? Meaning, let's put HB in layer 2, non-rotated, so 0 degrees alignment on top of layer 1. Excuse me. Now we have nitrogen atoms on top of nitrogen atoms, boron nitrogens on top of boron atoms on top of boron atoms. That's extremely uncomfortable for the system. So what it does instead is it shifts laterally such that it reaches an arrangement which is of AB stacking, meaning boron sits on top of nitrogen, or alternatively, BA stacking, meaning nitrogen sits on top of boron. And it turns out, if you look at this and you calculate this structure, either of these structures has a permanent electric dipole moment. In fact, if you can switch between the two structures, then you would have a ferroelectric switching, okay? And indeed, that's what we did, okay? So we made devices where we have parallel stack boron nitride bilayer, okay? We encapsulate, we place on top graphene. Graphene is now just a sensor to sense the ferroelectric state of this parallel stack boron nitride bilayer. We have, thicker hexagonal boron nitride just as a dielectric, and we have gates, bottom and top gates, to be able to apply an electric field in the perpendicular direction, so that we can now make a ferroelectric field effect transistor, okay? Where the state of conduction of the graphene, the resistance of the graphene, is going to depend on the polarization of this ferroelectric material, okay? And indeed, if you measure the resistance of graphene versus electric field, we see that it has this large resistance peak. Remember, in conductance it's V-shaped, in resistance it's a peak near charge neutrality. So we have the resistance goes up and down, and then if we sweep backwards, it goes up and down at a different place, okay? Which means this material exhibits hysteretic resistance, okay? We can do this continuously as a function of back gate and top gate. We can see how we go from having BA stacking configuration abruptly to AB stacking. And if we reverse, we go from AB stacking to BA stacking at a different electric field. Sometimes we actually catch it as a domain wall motion is sweeping through our contacts, so that we have these two states, given by two domains in some regions. Yeah. Now, that was for exact 0 degree stacking. We can actually also make a small twist angle. And in that case, we have a Moiré pattern of AB and BA domains, which now with an electric field, we can increase the size of one domain or increase the size of the other domain, okay? And indeed, if we fabricate devices, this is now twisted, bilayer boron nitride with a 0.6 degree rotation angle. Again, this is something we do on purpose. And now you can see that the resistivity, initially one domain is dominant. This domain now slowly decreases while the contribution from the other domain grows as the electric field is changed, so that then becomes dominant, okay? So now we have a gradual transition between these two domains, the contribution to the resistivity of these two domains, rather than an abrupt switch as it happens for 0 degree angle, yeah? Now, can we do direct imaging of this ferroelectricity? We can, okay? If you take one of these twisted samples and you look with vertical piezoelectric force microscopy, okay? These are images, phase and amplitude, directly imaging the electric field from the electric dipole moments of this ferroelectric behavior. And you can see the AB and BA domains in this beautiful honeycomb, pattern, okay? This is something that, again, was also done by two other groups independently. This thing is actually, all the other physics I told you about with superconductivity was at low temperature. This thing is actually robust at room temperature. You can cycle it thousands of times. You can wait months. The ferroelectric state, it's a good memory. This is in fact the world's thinnest out of plane ferroelectric, okay? It's less than 1 nanometer in thickness, and it's completely robust, okay? So now, as you can see there, we have basically infinite Moiré quantum matter possibilities, infinite of these Twistronic systems. Okay, we have hundreds of 2D van der Waals materials. Each of them individually can exhibit, different materials exhibit all the different phases that we have in condensed matter physics: insulators, metals, semiconductors, superconductors, ferroelectrics, magnets in 2 dimensions. Now we can place them on top of each other and modify completely their electronic properties, such that some of them which did not exhibit these phases, they exhibit them. In others which already exhibit them, they will get dramatically modified by this Moiré pattern, okay? Now, in order to do this, okay, I mean, my students and I, we have a lot of fun doing these things. It takes us to make one device, a month or so, okay? And we measured it for 1 year and we explore all the physics and all these correlations, and extremely interesting. But of course, it would be great if we can explore this infinite, phase space that we have here in a more systematic manner, okay? Rather than having thousands of grad students scotch taping and making these devices. For that, we need automation, okay? We need enhanced automated exploration of what are the most interesting combinations of materials and automated scalable nanofabrication of all of these materials, okay? And there's some concepts for how to do this. I'm part of a team which is called the QFlame Quantum Foundry for Layer Materials Exploration. We submitted a proposal to NSF, but they thought it probably was a little bit too risky. I think maybe a year or two later now, this thing is becoming more and more, a possibility. And I hope that, there will be funding in the future for this type of platforms to do automated, exploration of these systems. Now, I have to say that this is something which goes much beyond condensed matter physics and materials, okay? So people are now starting to look at these concepts, Twistronics, Moiré Magic, Moiré quantum matter, and realizing flat bands in other fields, okay? So for example, there are theoretical papers now exploring Moiré and twisted cold atom lattices and what, and you have, in some cases you can even simulate them without a twist, because in cold atoms, they have extra knobs to control the systems. You can also do this, this field of Moiré and twisted phononics. There are already experiments actually realizing flat bands and a magic angle bilayer phononic graphene, okay? You can also do this with photonics, okay? People have, because you can decrease the velocity enormously when you twist these layers, okay? You can actually slow light, make light go slow, and you can increase the density, optical density of states in photonic crystals by doing this, Moiré superlattices of photonic crystals. So this is something that goes even beyond, my field of condensed matter physics. So with this, I want to end by, thanking, acknowledging the great contribution of my group members. Okay, the work that I told you about was, mostly the PhD thesis of Yuan Zhao, also with contributions by, Daniel Rodan-Legrain and Jane Park, and the Moiré Ferroelectricity was done by Kenji and Shirui. But of course, all of my group members contribute greatly. We have many collaborators at MIT, Harvard. We get our HVN from NIMS, Japan, and of course, funding and support from federal agencies and various foundations. And I want to thank you for your attention. I'm happy to take questions.
Thank you, Pablo, very much for the very fascinating talk. So now we have a few minutes for some questions. Again, you can either raise your hand, directly ask your question, or you can type your question and I can help read it out. Okay, so I'm going to start with one question. A Moiré pattern emerges independent of angle. What is so special about the 1.1 degrees? Mm-hmm.
Very good question, okay? So indeed, Moiré pattern happens at any angle, right? The Moiré wavelength depends on what's the twist angle. Okay? And in fact, you can form a Moiré pattern at 0 degrees if your two lattices are not identical. So that's something that many people are actually looking at now, having two different materials at 0 degrees, but still a Moiré pattern forms. So at 1.1 degrees, what happens, is that essentially that, there is this competition between these two energy scales that I was mentioning in my explanation of the magic and graphene slide. One is what is the interlayer tunneling that creates that gap, this bonding anti-bonding gap. And the other one is, the energy scale at which these two bands cross between the Dirac cones of the two layers. And what happens at 1.1 degree is that those two energy scales become the same, okay? If you want, in some sense, an electron is as likely to go through its own graphene layer as it is to tunnel to the other graphene layer, okay? And in that precise moment, okay, there is a, if you want, that resonant process which leads to that flat band formation, okay? And that resonant process, it's, it's something which is very peculiar, okay? Not all systems have a magic angle, but it's not just graphene. There are a few systems that have that magic angle, okay? And it's something which many theorists are exploring, as they start to look at more and more materials and how to realize these flat bands.
So another related question, how do you measure the angle?
Very good. So it turns out that the charge density for which those insulating states appear, both the single particle and the correlated insulator states appear, are a commensurate, there are a number of electrons, they correspond to a number of electrons per Moiré unit cell. So if you know that density, then you know what's the unit cell. And if you know the unit cell, you know what's the angle, okay? That's one way of finding out. There's actually a more precise way of finding out, which is by performing magnetic field measurements, which tells you exactly, what is the precise density corresponding to that number of integer electrons per Moiré unit cell. But that's for, to go to the next digit. But to zeroth order, we can just do that by looking at what density do we have, the correlated insulator states and the single particle insulator states. And of course, people have imaged this afterwards with scanning tunneling microscope and other, scanning probe microscopies and found out agreement between these two methods.
Great. So a question about automated fabrication. Can you say more about the process, the cost, the technical challenges, and why it might be critical to advance the application of these new materials?
Yes. So there are two aspects of it. One is, as I mentioned here, we have hundreds of 2D materials. The combinations pairwise are millions. And if you add the angle, okay, now you go to infinite. Okay, so we have infinite possibilities to explore. So we need a theory telling us what combination is most interesting for a particular desired property. Okay, so what do I need to combine with what to get a certain phase of matter? Okay, so that is a process where we need a lot of, materials exploration. Then, rather than having, there's still going to be thousands of very interesting possibilities that we have to test. So rather than having one grad student 1 month each, to make one device, it would be great if we had a robot, an automated system that could make, for example, something that could take 1,000 pieces of graphene and now vary the twist angle by 0.01 degrees, from 0.1 to 2 degrees, so that we can make, 100 devices and then measure them all of them automatically and see, which one is better superconductor, which one is a better insulator, which one is a better ferromagnet if we align it to the hexagonal nitride, etc. So we need automation because otherwise it's going to take us too long, okay? Because making these devices right now, one by one, is extremely challenging. You have to think that, rather than graphene on graphene, think about putting plastic wrap on top of plastic wrap, and you need to get the angle between these two plastic wrap sheets perfect within 0.01 degrees and without bubbles and anything, okay? So again, it takes a lot of dexterity, and my students are extremely good. My students are postdoc at making this with high dexterity, but that's why it takes a month to do this thing for each device. If we had a robot, presumably, that could do this in an automatic way, if we get the robot to do it good enough, we could make hundreds of these devices in days, maybe, or in a month, rather than one per month.
Wonderful. So another question we have asks, what are your thoughts on the room temperature, high pressure superconductivity results from the University of Rochester in October 2020?
Very good. So I'm not an expert at all in this room temperature superconductivity. It seems that these superconductors are of the more conventional type. And I think, there are many experiments running. It seems quite good. The problem is that these superconductors are realized in various hydrogen rich materials, hydrogen sulfide, lanthanum hydride, etc., and that superconductivity is only reached at millions and millions of atmospheres of pressure, and in a very complicated, experimental apparatus. So it's from the physics point of view, I mean, it's interesting, but it's not very exotic because it is believed to be conventional type of superconductivity, which we think we understand more or less. And from the application point of view, it's not useful because this is something which is realized at extreme pressures, which you cannot, have in any type of device or in any wire or anything like that. So while I think it's a very interesting development, we have to, see if such superconductivity can be realized at ambient pressures and in regular materials that wouldn't disintegrate or etc. So it's a very interesting development, but I think that I'm not sure yet if that it's going to advance a lot the applications or the physics of superconducting materials because of those two aspects.
So this question is asking, when you talk about stacking layer over layer and rotating, chirality comes to my mind. Are there any chiral optical properties, or not optical, but due to the symmetry breaking, that would be interesting to study?
Very good questions. Indeed, these structures are chiral, right? You rotate angle in one direction, or you can rotate it in the other direction. In fact, let me see if I can go. You can see, for example, that this structure that we made here is actually not chiral. Here we rotate by angle theta and then by minus theta, okay? So it's mirror symmetric. And whether a structure is chiral or not, whether it has certain properties, it actually affects at a very deep level the properties of the system. In particular, it is believed that in order to have superconductivity, you need to have something which is called C2 rotational symmetry. It's a 180-degree rotational symmetry around an axis perpendicular to the graphene sheet, okay? But now going back to the chirality, indeed, these chiral structures, okay, they are very interesting physics that one can realize, nonlinear type of electronic and optical effect that one can realize in these structures. And the community is just now beginning to measure these type of effects. But indeed, it's interesting that it's a chiral structure.
Maybe we'll ask two more questions. There are many, many questions, but we're running out of time. So I'll end with two last questions. So Moiré patterns are representative of displacement fields from which you can determine strain fields. Have you thought how strain affects your properties?
Very good question. Actually, a Moiré pattern will form even if you don't have any strain, okay? So a Moiré pattern forms in all those diagrams that I showed. The Moiré pattern that formed, this is between two rigid lattices, right? I just drew those lattices, they're rigid. But you're right that actually, especially when you have very small angles of rotation between, let's say, these two graphene sheets, the carbon atoms like to adjust locally and relax the structure locally, okay? So there are indeed lattice relaxation that is present there so that the carbon lattices can accommodate more easily the preferred configuration. Strain, that lattice relaxation plays a fundamental role in the single particle gaps that isolate the flat band from the other remote bands. And having those flat bands isolated, it's very nice for its topological properties. So lattice relaxation plays a very important role. Now, in addition, on top of that, you can actually strain the lattices, okay? And in fact, these two-dimensional materials allows you to do something which is almost impossible to do in bulk crystals, which is to apply heterostrain, a different amount of strain to one layer with respect to the other. And theorists are now calculating all these possibilities. What happens when you strain magic and graphene? What happens when you apply heterostrain? And very interesting things happen, okay? The different phases of matter that magic and graphene can exhibit can change as a function of strain, okay? And you break certain lattice symmetries when you apply, for example, uniaxial strain, or when you apply several other types of strain. So it's one of the topics that my group is starting to explore now, actually, straining the systems, and it's very interesting. So yeah, I think there will be a lot more coming up on that.
Wonderful. So for the last question, and I apologize because there are quite a lot of questions, but we won't get to go through all of them. But for the last question, Could we dynamically tune the angle in situ during measurements?
Excellent question also. I wish so. No one has figured out how to do it yet, okay? It would be amazing. It would be it's one of the holy grails of this field, is to be able to tune in situ the twist angle. We can make any device with any angle that we want with pretty high accuracy by now. A few people have been able to change that angle in big steps at room temperature, but no one has been able to figure out how to measure it continuously, small angles at low temperatures in situ, so we can see all of these physics emerge, in situ, Ideally, you would want to do it electrically with some sort of actuator that would rotate these two sheets, okay? Now, this question couples very nicely to the previous question. It turns out strain plays or can play a similar role to twist angle in all of this physics. And strain is something that you can actually change in situ at low temperatures, okay? So a lot of groups, including my group, were trying to develop strain platforms for these 2D materials so that we can apply that strain, in situ electrically at low temperatures and see how we modify the behavior of the devices. I don't think anyone has done it yet, but strain has been applied to 2D materials before. We just have to do it now to this special Moiré systems, which is a little bit tricky, but yeah, I'm hoping that it will be done soon.
Great, thank you, Pablo. Thanks a lot for the fascinating talk. Thank you all for attending the seminar. Thanks, Pablo.
Thank you.